times 10 to the negative 5 Tesla. Alright, let's now look at what is called a solenoid. What is a solenoid? Now what I have here is a solenoid. It is made up of a number of while loops. Now what we're talking about so far is the field. Earlier on we obtained an expression for the field at the center of a loop of while. Now if you have several of those loops continuously wound on a frame, that is a solenoid. Now if you look at this, on the side that faces me, if the current goes up, the side that faces you, the current will go down. So if you use the right hand rule, let's work out the direction of the magnetic field when a current flows in this. If on my side the current goes up, I will wrap my fingers. See this? My fingers goes in on the right side, that is my right side, and comes out on the left. Now on your side the current goes down, so look at that again. The current goes down, wrap your fingers, my fingers goes in on the right and out on the left. And that's how the magnetic field of the solenoid is going to look like. So each side of a turn can be approximated as a straight wire carrying current. If on one side the current is up, the other side the current will be down. So the net field due to all these turns will be the resultant of the field produced by all these turns inside the solenoid. Now here I have a picture of that. Now you remember I've told you if the current goes up here, then the field will go, look at the way again, the field will go inside on the right and outside on the left. In the same way on the other side, again the field will go inside on the right and outside on the left. The result is you have a bar magnet here, is that right? Where the field enters the right and leaves the left. That means this end behaves like a south pole and this end behaves like a north pole. So the solenoid is like a bar magnet with a north pole where the current flows in the counterclockwise direction. If I stand here and trace the direction, look at that, the direction of the current is counterclockwise and that end is positive. If I stand here, the current will be clockwise when I look. So when you look from one side and trace the current, if the current flows counterclockwise, that end will be a north pole, and if the current flows clockwise, that end will be a south pole. Now this is actually an example of an electromagnet. You can see the field outside is rather weak and the field inside is very strong. Now using Ampere's rule, we can actually obtain an expression for the field inside the solenoid. I want you to watch the field lines inside. What can you say about the magnetic field inside the solenoid? All the field lines are parallel. That means the field inside the solenoid is a uniform field. It's a constant anywhere. And outside it is very weak. Now using Ampere's rule, we can show that the field at any point inside a solenoid is B equal to mu 0 Ni, where N is the number of turns per unit length. Number of turns per unit length. Don't confuse that. So N is the number of turns per unit length of the solenoid. Now notice here that B is uniform inside the solenoid and depends only on the number of turns per unit length and the current in the solenoid. Let's do an example. A thin 10 centimeter long solenoid has 400 turns and carries a current of 2 ampere. Calculate the magnetic field inside the solenoid. Well, what all we need is mu0, n and I. The total number of turns is 400 and the length is 10 centimeter. Therefore, what is the number of turns per unit length? Is the number of turns divided by the length, and that will be 4,000 turns per meter. And now we can use that formula right away. B, the field inside that solenoid, is mu0 Ni, and that will be 0.01 Tesla. Okay. A current carrying solenoid is actually an electromagnet. You can see this is an electromagnet, which is a solenoid, and this is a bar magnet, and look at the similarity. They are both almost the same. And such electromagnets are used as switches and relays in many electrical circuits, such as VCRs, automobile starters. You can see in all such electrical devices, these electromagnets play a very important role. So, if you want, you can actually go and study deeper by Googling electromagnets and their applications. Alright? Alright. Let's now wind up this lesson by talking about some theory about magnetism. You remember in the beginning of the last lesson I said all magnetic materials are made of these minute, tiny atomic magnets. And we call them dipoles, is that right? Made up of a north pole and a south pole. There are no magnetic monopoles. Now, what is the origin of magnetism? That is what we're going to discuss here. Now, an electric charge in motion produces a magnetic field. That's what we've been discussing so far. If an electric charge is moving, it has a magnetic field associated with it. Now, do you know that an electron is a spinning object? So, an electron that carries an electric charge is spinning, means it has a magnetic field around it. So, an electron carries a charge and a spin. It can be considered as a charge in motion, and so it has a magnetic field around it. In many atoms, electrons are paired in energy levels so that the magnetic field caused by one electron is cancelled by the magnetic field caused by the other electron, because their spins are in the opposite directions. But in some materials which has some unpaired electrons, those magnetic fields will not cancel. There will be some net magnetic field, and that can be influenced by external magnetic field. And also, if there are more electrons with spin in one direction than in the other, the atom will carry a net magnetic field. And this is the origin of the magnetic dipoles. Now, such an atom has a net magnetic moment. In some materials, these magnetic moments tend to align with one another, forming what are called magnetic domains. So, in some materials, most of these magnetic moments will align themselves to form domains. But ordinarily, the material will not exhibit magnetism because these domains are randomly organized. The direction of alignment varies from domain to domain. Now, here is an example. Here is the alignment inside one domain, and here is the alignment in another domain. If you take the behavior of the entire material, the net magnetism is zero because of the random arrangement of the magnetic moments forming the domains. Here is another example of these random arrangement of domains. But the moment you subject this material to an external magnetic field, all these magnetic moments, all these domains will align in the direction of the magnetic field like this, the diagram on the right. That means when a magnetic material like this is subjected to a magnetizing force is an external field. These magnetic moments will align themselves in the direction of the external field, making that object a magnet. So, when placed in an external magnetic field, the magnetic moments of the domain align in the direction of the magnetic field, producing a net magnetism in the material. Now, the extent of magnetization actually varies from material to material, and we use the term called permeability of the material to describe the extent of magnetization of a material when it is subjected to a magnetizing force. So we will now talk a bit about the meaning of permeability. Now, we have actually used it. The magnetic permeability of free space is what we call mu zero. Don't you remember that? Mu zero divided by 4 pi we used as the constant of proportionality. That mu zero is the permeability of free space, and you know it has a value 4 pi times 10 to the negative 7 Tesla meter per ampere. Now, most materials can be classified based on their magnetic properties as ferromagnetic, paramagnetic, and diamagnetic. Well, we will look at each of these briefly before we move on. Alright, what are ferromagnetic